In our first example, we will be solving the separable differential equation. And what we mean by separable is that we are able to manipulate this differential equation so that everything with a y is on one side of the equation and everything with an x is on the other side of the equation. So I'm going to observe that the dy is in the numerator on the left side of the equation. And so I want all of my y's to be on the left side and I want all of my x's to be on the right side. So I do not want this y on the right side, so I'm going to divide both sides of the equation by y. And I also do not want this x squared plus 4 to be on this side. So I'm going to divide both sides by x squared plus 4. And then I'm also going to move this dx. I don't want this dx to be on the left side of the equation, so I'm going to multiply both sides of the equation by dx. So I've done three things all in one step, which leaves me with the equation that would cancel out. On the left side, I would only have dy divided by y, because the dx would also cancel out. On the right side, I would have the x that was already in the numerator. It would be divided by the x squared plus 4 that we divided from both sides. These y's would cancel and there would be a dx at the end. So we've done all this algebra in the beginning just to start off and separate the variables. Now that we have the variables separated, we're going to come in and integrate both sides. The left side of the equation will integrate using natural log rule. So this is natural log absolute value of y. I'm not going to put the plus c here. I'm going to add the plus c on the right side when I integrate. To integrate the right side of the equation, I'm going to need to use a u sub. I will let u equal x squared plus 4, which means that du is 2x dx. We don't have that 2, so I can see that 1/2 du is x dx that we have in the numerator. So our integral is 1/2 the integral of du over u, which we know is 1/2 natural log absolute value of u plus c. So I will put that back inside of my integral for my antiderivative. I don't need the absolute value bars there because x squared plus 4 is always positive, so we could disregard that. I'm going to use a little bit of pre-calculus to simplify the right side. That 1/2 in front of the natural log, I could use the power rule for logarithms to send that to the exponent on the x squared plus 4. And if I have an exponent of 1/2, that's the same thing as the square root of x squared plus 4. Now I'm going to solve for y by using e on both sides of the equation. So when I put this e here, the e and the natural log will cancel out and just leave me with the absolute value of y on the left side of the equation. And of course I also need to put the e on the right side of the equation. When I do that, I can break up the right side of the equation into e to the natural log of x squared plus 4 under the square root multiplied by e to the c, because we had this addition in the exponents and we know we can break that up into multiplication with the same base. This e to the c, that's just a constant, so I'm just going to call that constant c, and I'm going to choose to write it in the front. Then here, this e and this natural log will cancel and just leave us with the square root of x squared plus 4. I'm going to drop the absolute value on y because the absolute value there really means that our answer could be positive or negative, but that will be determined by the sign of c, whether that constant of integration is positive or whether it is negative. So here we have our general solution. So in this example, we have another separable differential equation. So to get started, we're first going to observe that one term has dx in it and the other term has dy in it. Both of those terms are on the same side of the equation, so we're going to move one of those terms to the other side. It does not matter which term we move. I'm going to choose to subtract the xy dx term from both sides of the equation, and when I do that, I'm deciding to put all of my x terms on the right side of the equation. And I know that because now the dx is going to show up on the right side of the equation. So here is our new equation after we subtract that term over. So now we need to move things around so that only x's show up on the right side and that only y's show up on the left side. So I'm going to divide both sides by y. So I can cancel this y out from the right side of the equation, and I'm also going to divide both sides by e to the negative x squared. So I can cancel that out from the left side of the equation, which leaves us with y squared minus 1 all divided by y dy is equal to negative x divided by e to the negative x squared dx. Now we have the variables separated, but before I integrate both sides, I'm going to simplify the left and right hand side of the equations. On the right side, y squared minus 1 divided by y simplifies down to y minus 1 over y when we divide each of those terms by the y in the denominator. And then on the right side of the equation, I'm going to use rules of exponents to rewrite this e to the negative x squared in the numerator. Right now it has a negative exponent, so when we bring it up to the numerator, it will have a positive exponent. So it becomes e to the positive x squared multiplied by the negative x dx. Now I'm going to integrate both sides. On the left side, the integral of y is y squared divided by 2, and the integral of 1 over y is natural log absolute value of y. On the right side of the equation, we're going to need to use u substitution. To integrate, I'm going to choose u to be what is in the exponent of e. So u will be x squared, meaning that our du is 2x dx. We do not have a 2, so I'm going to divide both sides by 2 to see that 1/2 du is equal to x dx. We do have that minus sign there, so technically we're working with negative 1/2 du is negative x dx. So this negative x dx picks up all of that in the negative 1/2 du. So our integral becomes negative 1/2 the integral of e to the u du. Thinking back to Calc 1, the integral of e to the u is e to the u, so we have negative 1/2 e to the u plus c. Notice that I did not add plus c when I integrated on the left side. That's because I'm going to add plus c when I integrate on the right side of the equation. We only need to add c once. So now that we know what the integral is, I'm going to go ahead and sub back in what u is. So we have negative 1/2 e to the x squared plus c. So now we have this integrated. This is the general solution of the differential equation, but we were asked to find the solution that satisfies the initial condition that y of 0 is equal to 1. So that means that when I go in and replace all of my x's with zeros, I should also be replacing all of my y's with 1. So plugging in 1 for y in the equation and 0 for x in the equation, we have this, and at this point our goal is to solve for c. So we are left with 1/2 minus natural log of 1 is 0, and anything to the 0 power is equal to 1. So we have on the right hand side of the equation negative 1/2 plus c. I am going to add 1/2 to both sides of the equation to conclude that c is equal to 1. So now that we know that c is equal to 1, we're able to write the explicit form for the particular solution. So mind you, here, this is not our answer, but here at this point we have the general solution, and it's still general because we had not yet solved for c. Now that we have solved for c, I'm going to rewrite the general solution, and I'm going to replace that arbitrary constant of integration c with the value that we found using the initial condition. So I replace the plus c with plus 1, and here is our answer for the particular solution of this differential equation. In our next example, we again have a separable differential equation that we want to solve that is paired with an initial condition. The difference here is that they don't explicitly give us the differential equation. We have to read the problem and write the differential equation ourselves. So they want us to find the equation of the curve. So our goal is to find a particular solution. So we want our answer to look like y equals something. We want that curve to pass through the point 1, 3. So we know that when x is equal to 1, y is equal to 3 in that equation, and they say that it has a slope of y divided by x squared. It's important there that we remember from Calculus 1 that the slope of a graph is given by the derivative. So this here, when they tell us that the graph has a slope of y divided by x squared, that explicitly tells us that our differential equation is the equation dy dx, that is the slope, equal to y divided by x squared. So now that we have a differential equation, we're going to go ahead and separate variables. To do that, I'm going to divide both sides of the equation by y, and I'm going to multiply both sides of the equation by dx. So I have this equation here. I'm then going to integrate both sides. So I have the integral of dy divided by y is equal to the integral of x to the negative 2 dx. I just rewrote the right-hand side so that it will be easier for us to use the power rule when we integrate. Integrating on the left side, we get natural log absolute value of y. I'll add the c on the right side after I integrate x to the negative 2. Integrating will give me negative x to the negative 1 because we increase our exponent by 1 and divide by the new exponent, and then we add our constant of integration on there. So first I'm just going to rewrite this equation so it looks a little bit better. We have natural log absolute value of y is equal to negative 1 divided by x plus c. We're going to solve for y, so I'm going to use e on both sides of this equation. We've seen already that when we use e as the base of a sum, we can kind of separate that using rules of exponents. So that's what I'm doing here. In this case, like this a is this negative 1 over x, and this b is the c. So essentially I'm saying that e to the negative 1 over x plus c is the same thing as e to the negative 1 over x multiplied by e to the c. Because to combine these exponents, we would add them and get back to what we had originally. Now what we traditionally do here is the e to the c we write in the front, and that is just some constant. So I'm just going to write this as c multiplied by e to the 1 over x. And it's a negative 1 over x. So we have c e to the negative 1 over x. The y and the e and the natural log will cancel, and we can disregard the absolute value because it could be picked up in the sign of c, whether it's positive or negative. So here we have our general solution. We're going to take it a step further and use our initial condition that when x is equal to 1, y is equal to 3. So I will plug in 3 for y and 1 for x. And we're going to solve for c. So we have 3 equals ce to the negative 1. I'll divide both sides by e to the negative 1 to see that c is equal to 3 divided by e to the negative 1, which is the same thing as 3e, because we know we can move this up to the numerator if we change the exponent from negative to positive. So now that we know the value of c, we're going to go back to the general solution of the equation and write our particular solution that y is equal to 3e. That's our c value, multiply e to the negative 1 over x. Then the last thing I'm going to do is I'm going to use rules of exponents to simplify this. So I have y equals 3. The exponent on this e is 1, and the exponent on the e that it's multiplied with is negative 1 over x. So I'm going to add those together. So I'm doing 1 plus negative 1 over x. Common denominator would be x, and I would have x minus 1 in the numerator, because the 1 got multiplied by x over x. So we have that y is equal to 3e with the exponent being x minus 1 divided by x. And this is our particular solution.